this is our last problem, right? So using that, we have to obtain size of the test and the power of the test. It is a size of the test. It is expectation of phi of summation I 1 to n minus log xi, right, under h naught, which is equal to alpha, which implies a probability of summation I 1 to n minus log xi is less than k equal to alpha, which implies here we make some substitute transformation, right? So we can use that and write probability of 2 into summation I 1 to n minus log xi divided by 1 by theta plus 1, right? Then we can write it as theta plus 1, right, into theta plus 1 less than 2 into k into theta plus 1, which is equal to alpha, right? Which implies the probability of, this is chi square, right? Chi square 2 and degrees of freedom is less than 2 theta plus 1 into k equal to alpha. So here is a negative, right? Sorry, less than, right? So for that we have to make it as a greater than sign. It is probability of chi square 2n is greater than 2 theta plus 1 into k is equal to 1 minus alpha, which implies k equal to, what is then k value? K equal to chi square 2n 1 minus alpha divided by 2 into theta naught plus 1, right, under h naught, right? And here is theta naught, it is k equal to chi square 2n 1 minus alpha 2 into theta plus 1, right? This is a k value. Then we need to obtain the power of the test, right? That is power of the test, beta equal to expectation of summation phi of summation I 1 to n minus log xi, right, under h1, right? It implies the probability of summation I 1 to n minus log xi, which is less than k, under h1, right? Which implies the probability of 2 into summation I 1 to n minus log xi into theta plus 1 is less than 2 into k theta plus 1, right, under h1, which implies this is a chi square term, right? It's probability of chi square 2n, which is less than 2 into k theta under h1, then theta become theta 1, right? Theta plus 1, which implies the probability of chi square probability of chi square 2 in degrees of freedom is less than 2 into, what is the value of k here? K is chi square 2n 1 minus alpha divided by 2 into theta 1 plus 1, right? This is the value of k, right? Here theta 1 plus 1, which implies here to cancel, then probability of chi square 2n is less than chi square 2n 1 minus alpha into theta 1 plus 1 divided by theta 1 plus 1, right? Here in it's in the form of less than, right? So we have to make it as a greater than, that is 1 minus probability of chi square 2n, which is greater than equal to chi square 2n 1 minus alpha into theta 1 plus 1 divided by theta 1 plus 1. This is the power of the test in that problem. Okay. Next we will going to solve some and a problem. That is, question is given a random sample of size n from a distribution with the density f of x theta equal to theta divided by f of x theta equal to theta divided by x to the power theta plus 1, where x is greater than 1 and theta is greater than 0. For testing h naught theta equal to theta naught versus h1 theta equal to theta 1, where theta 1 is less than theta naught, construct most powerful test for testing h naught versus h1. Okay, here the question is given a random sample of size n from a distribution with the density f of x theta equal to theta divided by x to the power theta plus 1, where x is greater than 1 and theta is greater than 0. For testing h naught theta equal to theta naught versus h1 theta equal to theta 1, where construct MP test for testing h naught versus h1. Okay, then the solution is here is given that the density is f of x theta equal to theta divided by x to the power theta plus 1, right? F of x theta equal to theta divided by x to the power theta plus 1, where x is greater than 1 and theta is greater than 0, right? Then we can write this density as theta into e power minus theta plus 1 into log x. Okay, theta divided by x to the power theta plus 1, we can write it as theta into e power minus theta plus 1 into log x. Okay, then what is the likelihood? Like L of theta 1, theta x1, x2, so on, xn equal to theta power n e power minus theta plus 1 summation I 1 to n log xi, right? That is the likelihood function. Then here we need to obtain the most powerful test, right? For that we have to take the ratio of likelihood on the h1 and likelihood on the h naught, right? Here under h naught likelihood is theta naught x1, so on xn, which is equal to theta naught power n e power minus theta naught plus 1 log summation I 1 to n log xi, right? Then under h1 likelihood theta 1 x1 x2, so on xn equal to theta 1 power n e power minus theta 1 plus 1 summation I 1 to n log xi. So then we have to take the ratio, right? That is a likelihood on the h1 divided by likelihood on the h naught, right? Then theta 1 power n e power minus theta 1 plus 1 summation I 1 to n log xi divided by theta naught power n e power minus theta naught plus 1 into summation I 1 to n log xi, right? Which is greater than some k value, right? Then we can reject the null hypothesis, right? Which implies we can write this term as theta 1 divided by theta 1 power n into e power minus, here summation log xi is similar, right? We can take it as e power minus summation I 1 to n log xi into theta plus 1 minus theta naught plus 1, okay, which is greater than k1. It's equal to theta 1 divided by theta naught power n e power minus summation I 1 to n log xi here, theta 1 here plus 1 and minus 1, right? Here minus, then could cancel, then we can write theta 1 minus theta naught, right? It's greater than k1. It's equal to theta 1 divided by theta naught power n e power here, okay, this is the function of a random variable, right? So I have to take we have to divide by this term, right? We only need this term, right? For that, in the next step we'll divide by this term, then we can got e power minus summation I 1 to n log xi theta 1 minus theta naught, which is greater than k2, right? Now what is k2 here? K2 equal to k1 divided by theta 1 by theta naught power n, right? Which implies so here we will take the log, okay, take log on both sides, then you can get minus summation I 1 to n log xi theta 1 minus theta naught, which is greater than k3. What is k3 there? K3 equal to log k2, right? Which implies here we only need the summation log xi term, right? But here is minus 1 and also here theta 1 minus theta naught, so we can divide by this term. But here it's given that theta 1 is less than theta naught, right? Then this term is become negative, right? And you can write this as a summation I 1 to n log xi into this minus 1 into this term, right? Then here this is negative and this is negative, then this term is positive, right? Then we can write it as a summation I 1 to n log xi, which is greater than k4, right? What is k4 then? K4 equal to k3 divided by this term, that is minus theta 1 minus theta naught. Alright, this is a positive term, right? Then what is the rejection region then? Then the rejection region is summation I 1 to n log xi is greater than k, right? Then we have to write the test function, right? There is a test function for testing h0 versus h1 is phi of summation I 1 to n log xi is equal to 1 if summation I 1 to n log xi is greater than k, 0 otherwise, right? And here we need to obtain the value of k using the size of the test, right? But here we know that x follows this follows a density distribution with the density, and that is, what is that, f of x theta equal to theta into e power minus theta plus 1 log x, right? Then what is a log xi follows, if x follows the distribution with the density theta into e power minus theta plus 1 log x, then what is log xi follows? So here we need to find what is the distribution of log xi, right? For that we will take y equal to a log x, okay. Then what is x then? Here it is e power y, right? So we need to find the density of y, right? The density of log x, this density of y equal to f of x into Jacobian, right? Here what is the value of Jacobian? Jacobian is dx by dy, right? That is the modulus of dx by dy, that is e power y, right? Is e power y, right? And here it's equal to, what is f of x here? F of x equal to theta into e power minus theta plus 1 and log x, right? But here, what is the log x? Log x is equal to y. Then you can write here it as a y. Okay, then Jacobi e power y, right? And then combine that term, then you can get theta into e power here minus theta into y minus y, right? Then here plus y, right? Then minus plus got cancelled, then remaining e power minus theta into y, right? Here x takes the range is x is greater than 1, right? X is greater than 1, then here log is greater than 1 is what's the value then? That is y is greater than 0, right? Y is a positive, right? Then what is which distribution is this? Theta into e power minus theta y, where y is greater than 0. That is exponential with parameter theta, right? This is y, which implies y follows exponential with parameter theta. Then it implies the 2 into y divided by expectation of y, which follows chi-square 2 in degrees of freedom, right? That is 2 into y divided by 1 by theta, right? Which follows chi-square 2 in degrees of freedom, right? 2 into summation, right? Summation I 1 to n, 2 into summation I divided by 1 by theta follows chi-square 2 in degrees of freedom, right? Then using that we have to obtain the value of k, right? For that first we have to write the size of the test. Size of the test is equal to expectation of summation I 1 to n log xi, which is greater than k under h naught, is equal to alpha, right? Which implies the probability of summation I 1 to n log xi, which is greater than k under h naught, equal to alpha, right? Here you'll take a transformation, that is 2 into summation log xi is divided by 1 by theta, right? Less greater than 2 into k divided by 1 by theta, which is equal to alpha. Okay, which implies probability of here chi-square, right? Chi-square 2 in degrees of freedom, which is greater than 2 into k theta naught, right? Equal to alpha. Then what is the value of k? K equal to, which implies k equal to chi-square 2n into alpha divided by 2 theta naught, right? This is the value of k. Then using that we have to obtain the power of the test, right? Power of the test, that is expectation of phi of summation I 1 to n log xi, right? Under h naught, h1 is equal to beta, right? Which implies the probability of summation I 1 to n log xi, which is greater than k, equal to beta, right? Which implies probability of 2 into summation log xi divided by 1 by theta, that is a theta 1, right? Greater than 2 into k into theta 1 is equal to beta, which implies the probability of chi-square 2 in degrees of freedom, which is greater than 2 into k into theta 1, right? Equal to beta, which implies the probability of chi-square 2 in degrees of freedom is greater than 2 into, what is the value of k here? K is chi-square 2 in alpha divided by 2 theta naught, right? This chi-square 2 in degrees of freedom, 2 in alpha degrees of freedom divided by theta naught into theta, right? This is the power of the test in this problem. Okay, next we'll go and solve another problem, and the question is given random sample of size n from a distribution where the density f of x theta equal to theta into x to the power theta minus 1, where 0 less than x less than 1 and theta is greater than 0. Okay, for testing h naught theta equal to theta naught versus h1 theta equal to theta 1, where theta 1 is less than theta naught. Construct most powerful test for testing h naught versus h1. So this is the problem. Given a random sample of size n from a density that is f of x theta equal to theta into x to the power theta minus 1, 0 less than x less than 1, theta is greater than 0. For testing h naught theta equal to theta naught versus h1 theta equal to theta 1, where theta 1 is less than theta naught, construct MP test for testing h naught versus h1. So the solution is here the density is what's the density? Theta into x to the power theta minus 1. Alright, theta minus 1, 0 less than x less than 1, theta is greater than 0, right? So here we will write this density as theta into e power theta minus 1 log x. Okay, theta into x to the power theta minus 1, you can write this density as theta into e power theta minus 1 log x. Okay, what is the density then? Sorry, likelihood. That is likelihood theta x1 x2 so on xn equal to theta power n e power theta minus 1 summation I 1 to n log xi, right? In this case we have to take the ratio of likelihood, right? That is under h naught likelihood theta naught x1 so on xn equal to theta naught power n e power theta naught minus 1 summation I 1 to n log xi, right? Then under h1 likelihood theta 1 x1 so on xn equal to theta 1 power n e power theta minus 1 summation I 1 to n log xi, right? Then we have to take the ratio, that is ratio under likelihood, under h1 and likelihood under h naught, right? Is equal to theta 1 power n theta naught power n, it is e power theta 1 minus 1 summation I 1 to n log xi and e power theta naught minus 1 summation I 1 to n log xi, right? Which is greater than k1, right? Which implies you can write that as theta 1 divided by theta 1 power n e power summation I 1 to n log xi into theta 1 minus 1 minus theta naught minus 1, right? It's greater than some k value, which implies you can divide by this term, right? And then you can get e power minus summation I 1 to n log xi here theta, these are theta minus theta naught, right? It's greater than k2. That is k2 there. K2 equal to k1 divided by theta 1 divided by theta naught power n, right? Which implies here we will take log on both sides, right? Then you can get summation I 1 to n log xi into theta 1 divided by theta naught, which is greater than k3, right? That is k3 equal to log k2, right? Which implies here it's given that theta 1 is less than theta naught, right? Then this time is less than 0, right? Then summation I 1 to n log xi, which is less than k4, right? It's k4 there, k4 equal to k3 divided by theta minus theta naught, theta minus theta naught, right? Then here is given that x is lies between 0 less than x less than 1, right? Then what is the log xi? Then log xi is a negative term, right? For that we have to take the so this is a negative term, right? So we have to make it as a positive, right? So for that we have to multiply by -1, that is summation 1 I1 to n minus log xi is greater than minus k4. Okay, then this term become positive. Then the rejection region is summation I1 to n minus log xi is greater than k. Okay, then what is the test function? Then test function for testing h0 versus h1 is phi of summation I1 to n minus log xi, which is greater than k, is equal to sorry the test function for testing h0 versus h1 is phi of summation I1 to n minus log xi is equal to 1 if summation I1 to n minus log xi, which is greater than k, 0 otherwise. So here we need to obtain the value of k, right, using the size of the test. But here also we only know the density of x, right? That is the density of x is what's the density of x? Under h0, density of x is e power theta into e power theta minus 1 log x, right? So here we need to obtain what is the density of minus log xi, right? Minus, so for that we have to take y equal to minus log x. Okay, then what is x e power minus y, right? Then using that we have to obtain the density of y, right? That is f of y equal to f of x into Jacobian, right? Then what is the Jacobian value here? Jacobian equal to dx divided by dy, right? That is e power minus y into minus 1, right? That is, then you can get modulus of minus e power minus y is e power minus y, right? Jacobian is e power minus y. And here substitute the value, that is f of x equal to theta into e power theta minus 1 into log x, right? But here minus log x equal to y, right? Then what is the log x? That is minus y, right? Then Jacobian is e power minus y. Then simplify this down, then you can write these as theta into e power minus theta y, right? Here x is lies between 0 and 1, right? Then what is minus log x? That is y is greater than 0, right? Here y is greater than 0. Here density is theta into e power minus theta y, where y is greater than 0. Then what is which distribution is this? Exponential, right? Which implies y follows exponential with parameter theta, right? That is which implies 2 into summation I1 to n yi divided by 1 by theta, which follows chi-square with the 2 degrees of freedom. Using that we have to obtain size of the test and power of the test. This is your homework, right? So we have to obtain size of the test and power of the test using this transformation, that is y. If y follows exponential theta, then 2 into summation y divided by mean follows chi-square 2 in the case of 0. Okay, so size of the test and power of the test is your homework.